I teach a course here at George Mason whose audience is very special to me. It's for prospective elementary school teachers. And in that class, I start the class with a little quiz. Now, I had the Scantron guy come. I don't see him. So I think you're going to have to do this quiz just in your heads. Just 2 questions. Here's the first question. I want you to name a song or the title of a piece of music. So think about it in your head. And the second question is, name a theorem in mathematics. Right. Let me get some answers to the first question. Can you raise your hand and just name some, call on somebody? Yes?
Prelude in C# minor.
My goodness.
Maxwell Silverhammer.
Somebody else? Thank you. All right. On the second question, first of all, have you all gotten the same answer on the second one? No. What happens in my class is they tend to give the same answer in class. And the theorem they name is the Pythagorean Theorem. Or they can't remember a theorem, or they don't remember quite how to say it. So it's as though my students all said this. So I'm curious, how many actually did think of the Pythagorean theorem as the theorem? You know, you'd be fine in my class. I do want to state the theorem because I'll be talking about it a little bit later. A theorem has 2 parts. It's the hypothesis, what you're given, and the conclusion, what you have to prove. So in the Pythagorean theorem, it starts out with a right triangle, 90 degrees, sides A, B, and C. Still hypothesis. You put on each side of the triangle a square. So I've put square 1, square 2, and square 3 on the sides of the triangle. And the conclusion of the theorem is that the area of region 1 plus the area of region 2 is the same as the area of region 3. I think written this way, it's kind of surprising. Now you may have thought about this theorem a different way. If you notice, region 1 is a square of side A, and so its area is A squared. And region 2 is a square of side B, so its area is B times B, so that's B squared. And the third square, region 3, is a square of side C, so its area is C times C. And that's probably how you remember the theorem. I want to tell you another way to say the theorem with a little bit less symbols. You'll see why I'm doing this way in a moment. It says the sum of the areas of the squares on the sides of a right triangle equals the square on the hypotenuse. I guess I shouldn't chide you for naming the Pythagorean theorem as the theorem you all remember, because in fact it's part of our popular culture. In 1939, MGM made a movie called The Wizard of Oz, and in that movie, you may recall, the Scarecrow is concerned because he has no brain. He goes to the wizard, where it just says, you don't need a brain, you need a diploma. The wizard gives the Scarecrow a diploma, and upon receipt of the diploma, here's what the Scarecrow says.
The sum of the square roots of any 2 sides of an isosceles triangle is equal to the square root of the remaining side. Oh, joy! Rapture! I've got a brain!
Actually, we should forgive the perturbation of the theorem. He says isosceles triangle instead of right triangle and square root instead of square. But if you look at the credits of the movie, if you scroll down at the bottom, it says Scarecrow's theorem based on a real theorem in mathematics. So that's okay. So if in the question of the song, a natural question would be, can you sing the song a little bit, or can you write out the score, can you play it on an instrument? And my guess is you could do a piece of that. You might be able to sing a little bit of the song. And the question in mathematics is a little different. The question in mathematics I would ask you is, could you give a reason as to why the theorem is true? Could you explain the argument? That is, could you give the proof? So here's the first time we'll see this pairing. Statement of theorem, that corresponds to the title of the song. And the proof of the theorem corresponds to, can you sing the song, can you play the full score? But the question is, which of these comes first? For example, in music, which comes first, the title of the song or the singing of the song? Probably neither. Probably what happens, the slide you saw, is a composer might get an idea, might hum a few bars here and there, might get a mood of some sort, might create a motif, and the musician would start to hum a little bit. What about in mathematics? Which comes first, the statement or the theorem or the proof? In fact, the theorem and the proof are sort of paired. You don't have one without the other. In fact, a good definition of theorem is nothing more than a statement that has a proof. And so which comes first again in here? Probably neither comes first. Just like in music, you need to have sort of an idea. In mathematics, you have to have a guess about something, an inkling about something, and that thing's called a conjecture. Once you have the conjecture in mathematics, then you need to think about it for a while, because once the idea is there, the question is it correct? Is it leading anywhere? Is it a good idea or not? And so the technique in mathematics, once you have this inkling of an idea, is to think about what you've produced. I want to show you a little video about thinking in mathematics. The problem is it's not about math guys thinking, because the Big Bang Theory doesn't have any math guys on it yet. But I want you to watch what Sheldon and Raj are looking at as they discuss thinking.
We're doing serious research which requires complete and utter focus.
All right, let's buckle down and work.
And what are they looking at? Mathematics. All right, here's where we are. We have a statement of theorem, the idea of proof, and the idea of conjecture as sort of the core ideas in mathematics. But now I ask you, what is strange about what I just said? What's the puzzle? What's the question that ought to come to your head right now? I don't see a response. Here's my answer. How come these things weren't part of your education? Why weren't you taught the idea of theorem, proof, conjecture? Maybe you were. That's possible, so that's great. But my guess is for most of you, that's not what mathematics is. For most of you, my guess is mathematics is doing arithmetic problems, word problems, when do two trains crash together, factoring x to the 6 minus 1. But I'm telling you, mathematics is not just this. It's about these core ideas as well. When should you learn about these? Well, not never. Who should learn about them? Well, not no one, at least more than just math majors. So I ask you again, why wasn't this part of your education? This is an old question. It's been thought about long and hard. When and if to introduce these ideas into the math curriculum. I'm thinking about it in high school and middle school, of course. I've got some answers for you. We'll play the blame game. Let's see. We could blame it on the kids and why this is not part of your school. After all, kids learn abstract things at different rates, and they don't have a good attention span. And after all, it's more important to work on the basics and not the theoretical parts of mathematics. The problem about working with the basics, though, and not understanding why things are true, is students end up memorizing as opposed to understanding. We could blame it on the teachers, or maybe they don't know this stuff. So that's why they don't teach it. Or more likely, they may know it, but there's simply just no time in class to talk about it, because there's stuff they've got to cover in class, there's the standards of learning, there's multiple choice tests, and these ideas don't work very well for multiple choice tests. And so it's the teacher's fault. We could blame it on mathematics. After all, mathematics doesn't make a lot of sense. It's kind of abstract. I'm reminded I was telling a student something, and he responded back with something. I said, why is that true? And he said to me, well, that's one of the many things in mathematics that's true, and no one seems to know why. Okay, I've talked a bit about why is mathematics not what what it appears to be. I'll talk about what it is actually. If you went to a concert to hear one of those pieces of music that you mentioned, and you walk in, and all that happened was that you just saw the titles of the pieces of music, but they never got played, you'd be pretty upset. And so I want to make sure you get your money's worth here, and I want to sing the song of the Pythagorean Theorem. And what does sing the song of a theorem mean again? It's to give its proof. So I want to show you a reason why the Pythagorean Theorem is true. It's actually a fairly modern proof. Euclid's proof is much more complicated. It's a stop-action video, so I think you'll enjoy it. So let me remind you of the statement of the theorem. We need to show somehow that the area of region 1 plus the area of region 2 is the area of region 3. First step, pull apart all the pieces. Second step, drop down the region 3. Third step, erase the triangle. So these are the two regions I must show have the same area. There's a double diamond and the single diamond. I must show that areas are the same. That's the task. The next step is kind of clever. Put a square, a large square, around each of those two diamond-shaped things and label the sides. So notice, these two large squares are identical. They both have sides A and B. So the first square is A plus B by A plus B. The second square is A plus B by A plus B. One more clever thing, draw some diagonals. Now watch. The large squares have the same area, right? There are 4 triangles that are identical in each piece. If I take away those 4 identical triangles, what's left is this, and therefore these two areas are the same. Pretty clever, I think. All right, we now, back to the table, we now have 3, again, ideas: theorem, proof, conjecture, corresponding to title, playing the full score and humming a few bars. I want to talk more about conjecture now, because that's actually the more creative side of mathematics. Remember, conjecture is an inkling, a guess as to what's going on. To do so, to talk about conjecture, you need to have something to be thinking about. And so I have, in a moment, I'll show you what I want to spend some time thinking about. I should say, by the way, that in science, after you do an observation of some sort, the final product is a theory. And in mathematics, once you do an observation of some sort and do with the conjecture and proof, the final result is a theorem. So they're sort of paired together. Here's what I want to look at to explore the idea of conjecture. Little intimidating, I hope. It's supposed to be. Zoom in. Maybe it's more clear what it is. These are decimal expansions of fractions. You see them? Here they are in more detail. Here's a couple of them. So you remember half is 0.5 and a quarter is 0.25. Maybe you recall a third is 0.333 forever, right? And maybe you don't remember 1/6, but it also repeats a single digit from some point on. So that looks pretty okay, nothing terrible about it. And then we see this, 1/7. Random numbers, what's going on here? But in fact, they aren't random. If I highlight some things, you can see that in fact, every 6 numbers, the pattern repeats, right? So let's review these examples. We just talked about them over here. 2 more examples, a 13th and a 21st. Also offhand random, but not random. Again, repeats in blocks of size, what? Also 6, right? So maybe we're ready for a conjecture, a guess as to what's going on. What's the conjecture? Conjecture. The decimal expansions of 1 over n. What are the possibilities we observed? Stops, repeats a single digit, or repeats in blocks of size 6. That's a reasonable conjecture. The problem is it's, to go back to music, flat, discordant, wrong. Because look at 1/11. 1/11 does none of those things, but it does one of those things at least, right? At least it repeats in blocks of some size, in this case blocks of size 2. Well, our conjecture, while well-intentioned, ended up not working out, so what was wrong? 1/11 shows us wrong. In fact, the truth is a rather complicated theorem that I will not tell you. Actually, I will tell you a piece of it. I planned to, actually. All right, here's a piece of the big theorem. Hypothesis, n is neither even nor a multiple of 5. Conclusion, first of all, A, either. N either goes into 9, n goes into 99, or n goes into 999, etc. And B is the important one. The smallest number of 9s that n goes into is the block size. Now look, 11. Does 11 go into 9? No. Does it go into 99? Yeah. How many 9s are there in 99? 2. Block size should be 2. It is. So this theorem, makes the correct prediction. This is the statement of the theorem. I've not sung the song, nor will I. I've not given you the proof. But I did want to show you that the truth is a little bit interesting, a little bit complicated. Okay. I want you now to think back to your education in high school or middle school in a math class. My guess is class went like this for you sometimes. You get a new idea, and one of two things happens. Either you get it or you don't get it, right? If you get it, things are fine. Things are wonderful. If you don't get it, things are a problem, right? And of course, the more times you don't get it, the worse it gets, right? If you repeat, don't get it. Let me give you an example to illustrate this getting and don't getting. I think you get that x cubed is x times x times x. That's what x cubed means. And x to the fifth is x times x times x times x. Watch this derivation. So what's x cubed times x to the fifth? Well, I got first 3, then I've got 5x's. So how many altogether? I can do that. 8. The conclusion is x cubed times x to the fifth is x to the 3 plus 5, or x to the 8. I don't think that's complicated. Circle it, so we'll remember it. X cubed times x to the fifth, x to the 3 plus 5, or x to the 8. No problem. I think it's an I get it thing. And then this would happen. This is what happens to you one day in class. Do you remember that day? X to the minus 1. What could that possibly mean? I mean, how do you multiply x by itself negative one number of times? It's ridiculous. Good grief. Your teacher says, don't worry, here's what x to the minus 1 is. Oh, this is the I don't get it stage, right? I don't get it. I do want to point out this happens often to students with negative exponents, with younger kids with negative numbers to begin with fractions. I mean, you can count 1, 2, 3. What could 2/3 possibly mean? Negative exponents, imaginary numbers, infinite decimals. I mean, it sort of piles on itself where these new ideas come. And for many students, it's the repeated I don't get it idea that is detrimental to them. So your teacher then says, listen, here's the deal with x to the minus 1. Definition, x to the minus 1 is 1 over x. And that also seems ridiculous. I mean, why in the world should multiplying x by itself, negative number of 1 times, be 1 over x? I mean, I could have defined x to the minus 1 to be what I had for breakfast this morning, and then x to the minus 2 is what I had for breakfast 2 days ago, etc. I could do that, and I probably wouldn't. And I want to tell you why I wouldn't do that. I want to tell you why x to the minus 1 is defined to be 1 over x. Let me remind you of that thing I circled before. X cubed times x. You add the exponents, and you get x to the 8th. So let's look at x cubed times the unknown thing, x to the minus 1. It better be, if the formula works, if the pattern is similar, it should be x to the 3 minus 1, or x squared. That is x times x times x times something. The something is the x inverse. X to the minus 1 should be x times x. And what does that something have to be? Well, I've got 3 x's there. I want to kill one off. So I have to divide by x to get 2. And so if I take x cubed and divide by x, I get x squared. And so x cubed times 1 over x is since x cubed times 1 over x is x squared, therefore, one defines x to the minus 1 to equal 1 over x. This is to make that formula work. No problem. Problem goes away. So I've now named a fourth core idea. And these are the final 4 for the presentation: the statement of the theorem, the idea of proof, the idea of conjecture, and the idea of definition. I guess this is the second time Mason's reached the final four. Okay. So we've talked about why is mathematics not what it appears to be? What is it actually? The last section is called, why does all this matter? Well, if we were to teach these core ideas to our students, then, I got to read this, then more students will be motivated to truly understand mathematics. And these students could grow up to be parents who will motivate their children to do the same. And one of those kids could then develop the mathematics that would allow a theoretical physicist to propose a method that an engineer could use to design a cold fusion nuclear reactor which could produce virtually limitless, safe, inexpensive energy, thus saving the world from the ravages of poverty and the catastrophic effects of global climate change. I mean, what more would you want from a subject? And all because one day a teacher decided to talk about this. Thank you.